my research in surrogate modeling for design optimization. So also thanks, Simon, for introducing me to the participants. So my name is Pram, and I'm an assistant professor at the Faculty of Mechanical and Aerospace Engineering and at Institut Teknologi Bandung. So today's topic is a surrogate model, but I will focus more specifically on Gaussian process regression, which is my favorite surrogate model, and I use it a lot in my research. So this is the outline of my talk today. So I will start with the motivations. So why are we doing this? Why are we doing computational expensive optimization, and why we need surrogate models? And then I will talk a bit about the introduction to Gaussian process regression. And then I will talk about how to improve Gaussian process regression from two viewpoints. That is the covariance and also the trend function. And then I will also discuss about how we can use Gaussian process regression and also basically other types of surrogate model for design exploration. So besides optimization, we can also do design exploration, and I will show you how we do this by using Gaussian process regression. And then finally, I will talk about one of the applications on low boom supersonic wing design optimization. Although throughout the presentation, I will also show some applications. For example, when I discuss sensitivity analysis, I will also talk about some applications of this surrogate model. So a little bit about my background. So I come from the Flow Science and Engineering Research Unit. So we have two faculties here. So the first one is Dr. Lavi, and the second one is myself. So we are doing three big topics. So the first one is experimental fluid mechanics. So we are developing methods for modern fluid mechanics from the experimental side. And we are also developing a meshless computational fluid dynamics. So, okay, I should press this. As you can see that in the center, you can see that this is the result from one of our simulations by using the CFD code that we developed by ourselves. So this is meshless. So basically, you don't need to generate mesh, and you can simulate complex cases like this. And then the third one, which is the main topic of today, is design optimization. So I think you can see here that the topic revolves around fluid aerodynamics, or maybe other topics in fluid mechanics. So we are developing methods to handle flow science. For example, we are developing machine learning methods or surrogate models to handle design optimization in fluid-related case, let's say turbo machinery or wing design. So if you want to know more about the details of our research group, please visit our webpage over here, as you can see. So let's begin with the motivations. So the main keyword here is computationally expensive optimization, which is typical in engineering design. Because in engineering design, especially if we are in the detail phase or maybe also in the preliminary phase, we need computationally expensive solvers like CFD or finite element method. And this will be very expensive if we are considering more complex cases, let's say unsteady fluid dynamics or nonlinear computational mechanics. So the simulation itself, even for a single simulation, will take such a long time, maybe days or maybe also even weeks. And besides optimization, I also want to emphasize exploration, which is also important because frequently we don't want to just find the optimal solutions, but we also want to sweep across the design space. We want to know, let's say, the relationship between X1 and also the output, or we also want to know which variable is the most and the less important. So we believe that exploration is also important aspect of optimization. And optimization becomes difficult when, first, function evaluation is expensive. It takes hours, days, or even weeks. And the second one, and this is typical, that we don't have gradient information. So because we know that the location of the optimal point is when the gradient is 0. But how can we know that we reach optimal solution when we don't have gradient information? We cannot even use gradient information to guide our optimization. So this is when optimization becomes difficult, and to handle that problem, surrogate model is the key. And I believe that this is one of the most popular methods to handle computationally expensive problems in modern engineering design. A little bit about terminologies. So basically we have y, which is our target or our objective function. And we have fx, so y is a function of x, and x is our input variable. This is the true function, which is black box, meaning that we don't know the true relationship between x and y. And that is the reason why we need to use surrogate model. So as you can see that we have f hat there, which basically f hat tries to approximate our black box function. So this f hat is basically the main topic of today. So if you want to summarize my research in just a few characters, then basically that's it. Y is a function of x approximated by f hat x. And to create our surrogate model, we need our experimental design or design of experiment. So basically, we are picking some samples from the input space, and then we evaluate them by using computer simulation, let's say, and then we will use this information to build our approximation model. So machine learning basically also work this way, especially supervised learning. So surrogate model is basically one form of supervised learning. So you can see this from also the lens of supervised. So why surrogate-based optimization? Why not other gradient-based methods, which is not possible, of course, because we don't have gradient information? And why not other zeroth-order methods, such as pattern search or other local search? Or maybe why don't we just use the pure evolutionary algorithms without any surrogate model? Well, first, we want to do global optimization. And if we are using a pattern search, let's say, we are only doing local optimization. And you need to do that several times for you to arrive in the global optima. So we want to find the global optima at one shot. So we don't want to do something like multiple repetitions of local. And why not pure evolution algorithms? Because we have limited budget. Let's say only 100 simulations or even fewer. So these kind of situations where we don't have gradient informations and also we have expensive function evaluations is a perfect example where we should use surrogate models. Because surrogate model is basically an approximation model because you don't know the true function, you want to approximate this, and you will use that to do optimization or design exploration. Although I put some notes there that actually we can use this gradient information if you want to improve the accuracy of your surrogate model. So if we have auxiliary information, such as gradient information, then we can use that to improve the accuracy of our surrogate model. So as you can see on the right figure, so we have the blue points, which are our experimental design. We have our design variables, x1 and x2, and we also have our target or our objective function, which is CL/CD, which is the measure of aerodynamic performance. So we have several sampling points, and then we try to approximate that function by using this limited information. So that f hat is basically that response surface. So there are so many applications of surrogate models, but I am only listing two applications here because my research revolve around optimization, exploration, or uncertainty analysis. Although I don't think that I will talk about uncertainty analysis today because the time is limited. So I will focus more on design optimization and exploration. So like I mentioned earlier, optimization basically you want to find the global optimum or local optimum. The global optimum or local optimum. But in exploration, you want to know more. You want to know your effects. You want to sweep across your design space. You want to know the relationship between X and Y, or you want to know which variables are the most and least important. So Gaussian process regression is one surrogate model, and it's very nice, and it's my topic for today. And we can use this for many applications. But here I'll focus on design optimization and exploration. So a little bit about uncertainty analysis. So it's not an optimization problem, but what we want to know here is that we have random inputs. And we want to know how the randomness in the inputs affects the performance of our system. Because the inputs are also random, the output will also be random. And right now, we can use Gaussian process regression or any other surrogate model to approximate the random function. So basically, it's just that. So basically, it's still an approximation model, but the end goal is different. So for today, so I'll talk about Gaussian process regression, or in the engineering community or in the geostatistics community, they call it kriging. Okay, so unlike any other surrogate models, such as perfect regression, let's say, so Gaussian process regression is derived from a probabilistic viewpoint. So in this case, GPR constructs a surrogate model as a realization of a stochastic process. So we can say that basically GPR is a Gaussian random field. conditioned by the responses at sampling point. Because this is derived from the probabilistic viewpoint, we will have two structures. The first one is prediction. Of course, we are doing surrogate modeling. We want predictions. But secondly, we will also have information about how certain these predictions are. So in the figure below, you can see that we have the estimated function, the f hat, but we also have the uncertainty. And the uncertainties are zero at sampling points because you know exactly the values at these points, but the uncertainties are not zero at points where you don't have any information. So by using this information, we can do many math stuff such as Bayesian optimization or additive sampling. Okay, so basically it consists of two terms, the mean function. So this is our prior. So we can have a constant mean function or maybe polynomial mean functions. And then add this by the zero mean stochastic process, which is Gaussian. Then you will have your Gaussian process regression model. So below are the details, but we need information such as regression factor, regression coefficient, so we can use polynomials there. And then we also need to define our regression matrix, correlation factor, in which correlation matrix and correlation factor are defined by our channel function, or correlation or covariance function. So this is one illustration. So you have those red points, which are your sampling points. And then you try to approximate this by using Gaussian process regression with Gaussian kernel. Those blue lines are the sample paths, which is basically one realization of your stochastic process. And as you can see that the stochastic process is conditioned at sampling points. So then you will have these approximation models. So, and we also have the red line, which is basically the mean of that process. The mean of that process is basically your surrogate model. Because you have this many infinite number of random functions, if you average that, then you will have what are shown on the right figure. So what you'll have is the prediction, the f hat, and also the plus minus the standard deviation. So this is how we could know how uncertain our predictions. And this is based on the random field theory. Because as you can see also, one nice point is that at every single point, the distribution of the error is Gaussian. And that's why the name of this is Gaussian process. And one important part of GPR is the kernel function, which basically describes how much the outputs of two inputs change together. This is one important aspect of GPR that you need to define beforehand. So the role of the kernel function in GPR is different compared to when you use kernel function in supervector regression. In GPR, so basically kernel function encodes the covariance or correlation structure between input points. The idea is like this. When you have points that are close with each other, and then you evaluate the responses, you evaluate the y. So by common sense, we know that the values will not change that much. But the farther these points are, then the correlation will decrease because they are far from each other. So we encode that kind of common sense by using kernel function or correlation function. And there are many types of correlation function or kernel function, but I believe that the most popular ones are either Gaussian, Matten 3/2, or Matten 5/2. And as you can see that the formulations are different and all of them are the function of length scale. And this is one hyperparameter that you need to tune to create a good GPR model. So first you need to pick your kernel function. The second one, you need to optimize your length scale. And on the red figures, you can see, and these pictures, I took this from Rasmussen's book, Gaussian Processes for Machine Learning. You can see that each kernel function is different. And the stochastic processes generated from each kernel function is also different. So we can see that we have the Gaussian correlation function, which is the green one. You can see that the stochastic process is smooth. But when you change the kernel function to Matten 3/2, then the process is quite smooth. Basically, it means that if you change your kernel function, then you will have a different accuracy of your Gaussian process regression. In the figure below, you can see that if we change the kernel function, then the accuracy will also be different. So picking a good kernel functions is also key in creating a good Gaussian process regression. And how do we obtain this exact surrogate model? Let's say that we already picked one kernel function, Gaussian, let's say. And how do we pick the theta, the length scale, which is also multidimensional? So we do that by either one of these two methods. The first one, which I believe is the most common, is that we perform maximum likelihood estimation. So what we are doing there is that we have to maximize the likelihood function. Or just like any other machine learning models, we can minimize the cross-validation error. But likelihood methods is more resistant to overfitting, which I think is one of the reasons why Gaussian process regression is frequently optimized by maximum likelihood estimation. So I think you can see one issue here is that we need to pick the good kernel function. Because if you wrongly pick kernel function, let's say that you use exponential kernel here, then you can see that the accuracy is poor compared to if you use Gaussian kernel function. So let's say that we want to use GPR, then we can use that for optimization. Basically, it's approximation models, and you can use that for virtually any type of optimization methods. And the first popular method that use GPR is Bayesian optimization. So it's a sequential optimization that takes into account two important structures, which is the prediction and the uncertainty structure from GPR to update the model sequentially so as to find the optimal solution. So the keywords, we have two keywords, sequential and also uncertainty, and basically that is Bayesian optimization. But we can also use this for other methods like evolutionary algorithms, because you can also find in the literature that we also have the Kriging assisted evolutionary algorithms, or maybe the Kriging based particle swarm optimization. And maybe you can also find Kriging assisted CMIS. So there are so many applications of GPR in optimization methods. And what I want to emphasize here is that the accuracy of the model is also important, especially if you are considering global optimization, not just for optimization, but also for exploration. Because in exploration, you want to sweep across your design space. So it's very important for us to have a good accuracy. Okay, and below you can see an illustration of Bayesian optimization. So here you can see that at each iteration, you optimize the so-called acquisition function, in which you can see that it takes into account the information of both the prediction and also the uncertainty. And then you evaluate the sample suggested by your Bayesian optimization, and then add this to the standard experiment, and then repeat it until you are running out of computational budget. So you can see this, that even though the expression looks simple, we can do many things by seeing these equations. The first one is that you can improve the mean function. You can improve your prior here by using, let's say, empirical models or maybe polynomial trend functions. Because the most typical approach is that you just use a zero mean function or maybe just a constant trend function. But in engineering, typically you can improve this by using polynomial models. Or you can improve the stochastic process by, for example, changing your kernel function. Or if you want to, you can include the derivative information of your objective function with respect to your inputs in your kernel function. Or you can do composite kernel, which I will talk about today. And you can also do many things. You can incorporate even physical law or governing equations of a fluid or a structure, let's say, multivariate simulations to the Gaussian process regression. So one keyword here is that Gaussian process is very flexible and versatile. So let's view this Gaussian process from one viewpoint. I want to show you that we can improve Gaussian process regression by improving the stochastic process. So one way to do this is to design a better covariance function or correlation function or kernel function by composite kernels. The reason is this, because we have a number of kernel functions, Gaussian, pattern kernels, exponential, and other kernel functions, and we need to pick one best kernel. So the idea of this research is, instead of picking just one kernel, how about if we combine multiple kernels so as to create a better and better Gaussian process model? So the technique proposed in the paper, which is published in the IEEE journal, aims to combine multiple individual kernels to construct a more accurate Gaussian process model. And the way we do this is by combining these kernels in the form of a weighted sum equation. So because in Gaussian process regression, we need to optimize the hyperparameters such as length scale or the regression factor and also the coefficients of the polynomials. Here we add a new set of hyperparameters, which is the weight of kernel function. So this is the weighted sum combinations of kernels. You can see the figure on the right side that we have the individual kernels, and then by weighted sum formulation, then we can find new kernel function, which is the combination of the old kernel functions. But we cannot just use a random combination. We need to optimize it, which is the idea of this method. The idea is that we also treat the weights as hyperparameters so as to maximize the likelihood function. So we experimented with many real problems, so many CFD-based methods because we are dealing with fluids. Like for example, in this case, for details and other problems you can see in my paper. So this is a two-dimensional problems. This is a turbomachinery problem with two inputs, which is the swap and twist of your blade. And the quantity of interest is the adiabatic efficiency, and this is quite expensive. We need about 6 hours or 7 hours for evaluating just one combination of the descent variable. So we evaluate this by using Reynolds average Navier-Stokes CFD, and then we evaluate several samples, and then we compare Gaussian process with one kernel function or the composite kernel learning, and MS there is a model selection. Here you can see that the errors of the composite kernel learning are lower than the individual kernel function. Basically, it is not just picking one base kernel function, but even more, you combine these kernels to create better kernels, and this is the idea of composite kernel learning. So the take-home point here is that instead of picking just one kernel, we can combine them. We can combine them, and we can even create a better Gaussian process regression model. Then we'll move to the second part. And of course, this is just one method. We can do many other methods to improve the stochastic process, let's say. But now I will talk from the viewpoint of the mean function. And the idea here is that we need to design a better trend function. And what I want to show here is that in some applications, we have the gradient information, and we want to build a surrogate model because we want to design exploration. So what we did is to create a better trend function by using the so-called gradient enhanced polynomial chaos regression. So polynomial chaos is basically like your polynomial regression, but we use orthogonal polynomials because of several advantages when you use orthogonal polynomials compared to if you use the standard monic polynomials. So here, what we did is that we improve not just the stochastic processes, but also the regression or mean functions. Because the conventional way to do this is by assuming that the mean function is 0, but you improve the stochastic process by using gradient information. But what we did here is that we improve both the stochastic process and also the trend functions by using the so-called gradient enhanced polynomial chaos regression. So what the key point here is that instead of having just a constant trend function, we can use a gradient enhanced regression model to better approximate the trend function. And this is fully automatic. I mean that you don't need to really pick the polynomial basis by yourself because this is automatically done by an algorithm called least angle regression. And let's try that on one difficult problem, which is only 4-dimensional, but the problem is highly nonlinear. So this is called the blended wing body problem, and the output is drag coefficient, and the inputs are Mach number, angle of attack, altitude, and the last one is tail angle. So 4 inputs, but the problem is highly nonlinear. And if you compare our method, which is called the gradient enhanced polynomial chaos kriging, sometimes you can see that I use Gaussian process regression, sometimes I use kriging. Maybe I'm not too consistent, but basically they are the same. So sometimes I use kriging, sometimes Gaussian process regression. So in this function, we can see that compared to the gradient enhanced kriging, which is GEK over there, you can see that we have better approximation accuracy. So instead of just using a constant trend function, nicely the idea of having a gradient enhanced trend function really improve the accuracy. So in summary, the result shows that the proposed method successfully outperformed the conventional gradient enhanced kriging. So this is one example where you can use the gradient information to build a more accurate surrogate model. And even more, we can fully explore that gradient information to create a more accurate model by using this method. So of course, I have more research, but I was highlighting those two because I want to show how we can improve the Gaussian process regression from the viewpoint of the covariance function and the trend function. And then let's move into the next topic, which is GPR for design exploration. And this is related to optimization, but different. Oops. Okay. Because what we want to know here is more than optimization. We want to take a peek at our design space and our objective functions. For example, here we have X, which is our design variables. We want to answer questions such as this. Which X influences FX the most? Or maybe you also want to answer questions such as, are there any non-influential variables? Or can we reduce the dimensionality? Maybe the problem is high dimensional, but that is maybe only an illusion. Maybe the problem is at best 2 or 3-dimensional problem. And the next information is also important because we want to know whether the function is linear or nonlinear. And this is the goal of design exploration. So we can do that by several means. For example, we can rank the variable via a global sensitivity index. So by this, I mean that by looking at this bar plot, we can see that some variables are more important than the others. Or we can also do things such as transforming the coordinate or rotating the coordinate. And then you can see in this plot that I think in this problem, it's like an 8-dimensional problem. The figure in the center, I mean, if you smartly rotate the coordinate, then basically the function is effectively 1 or 2-dimensional problem. And then the third one is we can do a relationship analysis by using techniques such as self-organizing map, parallel coordinate plot. Basically, the goal is the same. We want to know which variable are the most important, least important, or we also want to know the relationship between variables in the Pareto optimal solutions. So I'm a bit a fan of global sensitivity analysis. If let's say that an optimization problem comes to me, the first thing that I want to do is to do global sensitivity analysis because I want to know the complexity of the problems. And also I want to know which variables are the most and the least important. I want to rank the contribution of the variables to the objective function. And global sensitivity analysis is the best way to do that. And there are many variants of global sensitivity analysis methods, but I believe that the most popular one is the variance-based decomposition, which works by decomposing your functions into the following. So basically, you are decomposing the function into the mean term, the main effect, in which the main effect is just a function of either x1, x2, or xm, let's say. And we will also have the interaction terms, which is the interaction between variables. Interaction between x1, x2, interaction between x1, x2, x3, and so on until you have the nth order interactions. Although typically we only care up to the second order interactions. It's very rare that people consider things such as 7 or 8 order interactions because we have the principle of compressibility here. So once you decompose this function, then you can also decompose the variance. You have the total variance of your function, but you will also have the partial variance of each term in the Sobol decomposition. The previous one is called Sobol or ANOVA decomposition. You have the partial variance, and then you have the total variance. Because these terms are orthogonal, so you can evaluate the so-called Sobol index. So basically, by evaluating the so-called Sobol index, you will know the contributions of the main effect or the interactions to your outputs. So in that case, you can answer questions such as, are there any interactions between variables? Or you want to answer questions such as, is x1 is more dominant than x2? We can answer that questions by using Sobol index. So total Sobol index and Shapley effects are just different way of how you further evaluate the Sobol index information, but basically they want to rank the contribution of your variables to the output. I will show you one example later. But the problem is evaluating Sobol index or Shapley effects is very, very expensive. And the way you need to do that is by using Monte Carlo simulation. But again, that is very expensive. So the idea goes like this. Replacing your black box function with surrogate model. So the idea is always the same. You replace your black box function with your surrogate model. And then after that, we can use Monte Carlo sampling on this F hat. Then we can evaluate the global sensitivity analysis in this. So I need to remind you that I think if you are using libraries such as sklearn, you can find that methods such as random forest have their inherent feature importance. But what I'm explaining here is quite general, meaning that it's model agnostic. You can use any other surrogate models to evaluate the global sensitivity analysis. So after you have your surrogate models, you can just use Monte Carlo simulation, Monte Carlo sampling to evaluate the main effects, interactions, or total Sobol index, or Shapley effects. See that the idea is simple, right? You are replacing your function with a surrogate model, and then you use this surrogate model to evaluate your sensitivity index. This is just one example. This is the so-called Ishigami function, which is a sinusoidal function. It's highly nonlinear. So here what I'm showing to you is that we can evaluate the Sobol index by using supervector regression in this case, and we can also do bootstrapping to evaluate how uncertain our predictions are. Because if we evaluate our Sobol index or our or other global sensitivity analysis, we should also inform analysts how uncertain the predictions are of our Sobol index. Then to that end, we can use bootstrapping method, for example. So the previous one was Sobol index. But like I said, there are many methods for design exploration. And one particular thing that I like is the so-called active subspace method, which is basically a low-dimensional representation of your function that explain most of the variability of the function. So you can say that this is the direction with the highest variance. So how do we obtain active subspace? The way we can do that is by rotating your coordinates. So basically, you need to perform coordinate transformation from your original input space. So the way we can find the rotation matrix, the W over there, is by finding the covariance matrix of your gradient information. The covariance matrix of your gradient information. So yeah, gradient appears there. So, but remember that if we use surrogate models, we can just cheaply evaluate the gradient information of that surrogate model. And this active subspace is very nice because you can do things like this. Let's say that I have this problem. So this is my past optimization problem. We have 10 variables that alter the geometry of your airflow, which is the cross-section of a wing. So I had a question like this. Okay, it's 10-dimensional problem, but the question is this problem really high-dimensional? And what I did was that I used Gaussian process regression to approximate the original 10-dimensional problems. And then I applied active subspace to this original input space. Then I found the W matrix to rotate my coordinate. And then I found that basically the problem is effectively two-dimensional. Then I answered questions such as, is it nonlinear or not? Then I found that this one is nonlinear because it's not just a constant monotonous function, but it has some peaks like this. And is it really 10-dimensional? Then I found that the problem is basically essentially a two-dimensional problem. And is it unimodal or is it multimodal? Then by smartly rotating the coordinate, then we found that the problem is basically a unimodal problem. So we are taking a peek at the complexity of our problem, and we can do that by several means, by global sensitivity analysis or by methods such as active subspace. So basically, we want to take a peek, we want to go deeper into our functions because we want to gain, for example, design insight or design rules. And that's basically, I believe, the goal of engineering design. Optimization and also exploration of the design space. So uh, the last topic is the application on low boom supersonic wind platform design, and this is very recent, published in 2021. Okay, so this is a collaboration with Tohoku University. So the goal is to design a supersonic wing transport that reduce both the drag and the sonic boom loudness. Because if you are designing a supersonic aircraft, you concern not just on the drag coefficient, but also on the sonic boom loudness. Because in the future, what we want to design is a supersonic transport with low drag and so low loudness. So we want to design a wing platform that accomplish those two objectives. So we were using GPR, surrogate model, and also the EHVI, the expected hypervolume improvement as acquisition functions, and also for parallelization, use the so-called Kriging believer. And we ran this on a Tohoku University integrated supercomputer system. So we evaluated a 6 variable and the 11 variable case. But what I want to show you here is only the 6 variable case. And we use many softwares, including our in-house GPR, point-wise for meshing, and simulation using the Tohoku aerodynamic solver, and software from NASA to evaluate the noise. So let's do the sensitivity analysis first. And it turns out that although it looks like that the problem is 6-dimensional, but 2 variables are not important. The X and Z location of the wing are not so important. So the problem is effectively 4-dimensional. And even more, if we see the lift coefficient as a function of the 6 variables, it is effectively a 2-dimensional problem. Only the chord of the wing and also the sweep of the wing affects the lift. So if you do something like plotting C1 and also the sweep of the wing with lift, then you can see that the problem is basically 2-dimensional. And for drag, it's like a 3-dimensional problems. For loudness, it's also a 3-dimensional problem. So this is how we can utilize information to take a peek at our design space by using global sensitivity analysis. Then we did optimization, of course, because the topic of this talk today is optimization. And then I will not talk in detail about this, but we are happy that we found some interesting designs that hopefully will be the candidate of new supersonic transport. But what I want to emphasize here is that what we gain is the knowledge that can be used later for designing a better supersonic transport. For example, here we found designs that minimize the drag, but the design with minimum drag is not the design that minimizes the boom. Okay, so we obtain this by using multi-objective Bayesian optimization assisted by the Gaussian Process Regression surrogate model. So the lesson learned from this case is that, yeah, we were happy because GPR made the design feasible and efficient. And we use this not just for optimization, but also exploration. So, but the thing is that it was difficult to be fully automatic. I mean, we wanted something like we press enter, and then after a few days, then the computer give us back the optimal solutions. But there were technical problems, such as the problems in the meshing or some solution didn't converge. So sometimes we must stop for correcting possible errors. So I think we cannot say that the process is fully automatic. And post-processing of the optimal solutions is also important because what we want to gain here is not just the optimal solution, but also why those solutions are optimal. We want to gain design insight. Okay, I don't think that I need to discuss it because I think I already discussed why we are using Gaussian process regression. So some closing thoughts. So the GPR, I believe that is a very useful and versatile surrogate model In fact, we already use this for many applications, not just optimization, but also exploration, uncertainty analysis, and also some machine learning related stuff. So post-processing is very important. So if you find optimal solutions, us as an engineer need to analyze and uncover the mystery of why these solutions are optimal. And then if you can evaluate auxiliary information such as gradient, then do it and then use that to improve the accuracy of our models. So maybe one will ask, what is the future of GP? So my take on this is that I believe that deep Gaussian processes is one of the most promising surrogate models, but it is too complex and then it has more and more hyperparameters compared to the, let's call it the standard Gaussian process. Adaptive sampling is very important. So a proposal of better learning criteria or a better acquisition function is always welcome. And then this is also one of my current research directions is that we want to incorporate physical information into our Gaussian processes by changing the kernel functions or maybe also the trend function. So I believe that physics-informed Gaussian processes is one of the most potential research directions. And that is the end of my presentation. And I want to acknowledge my collaborators in GPR and also my students. So these guys are people who collaborated or collaborating with me to create a better GPR models or apply GPR models on some real engineering applications. And also thanks to you for attending my presentation. I hope that I can give you some new insight about how we can use GPR in engineering design. So thanks a lot.
Thank you, Prem, for this very insightful talk, covering very important aspects of using GP in design, optimization, and exploration. So for all the participants, we are now open for some discussions. If you have any questions to the speaker, feel free to raise hand or unmute yourself and ask a question. You can also type in the chat box if you like.
All right, let me go first.
Yeah, right.
Hello, Faye.
Yeah, good to listen to your talk. Two questions straight up. The first one relates to the sonic boom example that you talked about.
Yeah.
Did you encounter any failed simulations? And did you have to deal with any failed simulation?
Oh, failed simulations.
Yes. And how do you deal with it? Or did you exclude that data? I mean, did you do anything special in that?
Okay. Okay, so let me answer that question. Yes, we did encounter failed simulations, but there were several types of failed simulations. The first one is that the failed simulations that I don't think that we can do anything more with these failed simulations. And for that case, we just throw them away. But there were some simulations that we think that I think we can still continue with this. So that's why I said that the optimization was not fully automatic, because let's say that we have some simulations that look failed, but after we refine the mesh or after we did some corrections, we can finish that solution. It will converge, and then finally we found that we can use this to further enrich our design of experiments. But there were some simulations that we cannot do anything more with these simulations, so we just throw them away. So we were not doing process such as computing. So basically, if there are failed simulations, then we'll take a look on that simulations. Maybe we can do something on that failed simulation. And I hope that answered the question.
Yeah,
Ray.
thanks. And the second one, yeah. I understand that you talked about identifying the relevant variables, and you have talked about the 6 being brought down to 3. And when you build your model with those 3 and undertake an optimization exercise, you would get the optimum values of those 3 variables. What are the variable values for the remaining 3 variables? Are they set at mean when you generate the configurations?
Okay. Okay, thank you for the question. When we did optimization, we used all the 6 variables, because I have to be honest here that we did this process after we finished the optimization. And then we realized that some variables are maybe not that important. But let's say that we do it first before we do the optimization. So my sense will tell me that I have to do optimization by using still all the 6 variables, because 6 variable is not that even high. Maybe if I have 100 dimensional variables, I want to reduce the number of variables. But here we were using all the 6 variables. Because as you can see here, also that the X and Z in terms of the loudness, they maybe contribute, although even a little. If we include these variables, we can even find a better optimal solutions, although maybe on this slide. And also here, some variables that are important in one objective functions, some important variables maybe are not important in other objective functions. Let's say that the T1 here is not important in lift, but T1 is important in drag and loudness. So we have to be careful because we have to see this from many viewpoints. And then about the values of X and Z, unfortunately, I didn't check that. So I cannot really answer the question for now. But I believe the values will be quite random because they do not affect the objective function.
Sure. Thank you.
Thank you, Ray.
Mamun, you have a question? Mamun, can you unmute yourself? Let me try.
Can you hear me now?
Yes, yes.
Hi, Prem. Thanks for the talk. I just have a quick question about, so when would you think we should think about the active subspace? For example, what would be the criteria? So when we deal with, say, for 50 variables or 100 variables, so for example, you've shown only 6 variables, you deal with that, right? So when we go about any kind of optimization problem, we don't necessarily know about these variance measures. So, when should we think about doing active subspace reduction?
Okay.
And another thing, so how many variables do you think the GPR would fit properly to what extent, say 10, 15, 20?
Okay. Okay, so thanks, Mamun, for the question. So the first question is about the active subspace, right?
Yeah.
So, so how to identify the number of variables, the number of active variables? So the way we do that is when we evaluate the covariance matrix of the gradient, then basically the W there is eigenvectors. So each eigenvector has the corresponding eigenvalue. And this eigenvalue basically telling us how important those variables are. So typically, we always sort the eigenvalues. So if there's a jump in the eigenvalues, then that basically means that the next variable are not important. So let's say, I think the rule of thumb is that we need to keep at least 99% of the important eigenvalues. And if your problem has a low dimensional subspace like this, then 2 or 3 variables are enough. But the thing is this, when I did this problem, I still used the 10 variable for optimization. And remember that this reduced space is not obtained just simply cutting the number of variables. You rotate your variables. So basically, maybe those 10 variables are still important. But when you try to rotate the coordinate, then you find that there are only 2 effective dimensions. So this kind of process informed me about how complex my problem is. For example, then I found that the problem is nonlinear. Then I have a better confidence in using Gaussian process regression because I'm not modeling a very complex model. And also, I know that the problem has low effective dimension, meaning that the problem is less complex than what I thought. And then finally, it's unimodal. So I don't really need to do, let's say, a multi-step gradient optimization, let's say. So this informed me about how complex my problem is, although I know that some people are using this information to build a surrogate model in the reduced design space. And for your next question about the dimensionality, it really depends, because even though if your problem has 30 dimensions, if it only has 2 important variables, then actually your Gaussian process will be a good approximation. But if you have a 30 dimensional problem and each variable is important, then it's still enough to use Gaussian process regression. But usually I use Gaussian process regression if I have a maximum 20 or 30 variables. If I have something like 50 variables, then usually I use the polynomial chaos expansion regression, because you have 50 variable models, and instead of capturing the locality of the problem, I want to know more about the global trend of the function. So that is why in high dimensional problems, usually I use the polynomial chaos expansion model. So I hope that answered your question, Mamun.
Yep. Yeah. Thank you.
Thanks for your question.
Thanks, Pram. So Ali had a question. Ali, please go ahead and unmute yourself. And
Oh, in the chat. Okay.
Hello. Thank you for your presentation. I just had a question when you mentioned that you are using a combination of kernel functions on slide 19, I think. And so I assume that each extra kernel function has another hyperparameter that should be optimized. So actually you're providing more flexibility for your kernel function, and these, I think the number of these DOE points actually at least should grow linearly with the number of these hyperparameters. Otherwise, you have the risk of overfitting. So I just wonder, how do you avoid the problem of overfitting?
Okay, so thanks, Ali. That was a good question. So we experimented with 2 types of composite kernel learning. So that's why you can see that we have CKL and CKLF. So F here stands for true. So in the composite kernel learning without F, so basically we only combine the kernel functions into one kernel functions, but they share the same length scale. So in that case, if we are considering a composite kernel learning technique, then we only add k hyperparameters, and k is the number of kernel functions. So if we have 4 individual kernel functions, then we will have an extra 4 kernel functions. But composite kernel learning technique full there is more complex, because in that case, we use a separate hyperparameters or length scale for each kernel function. So the number of hyperparameters becomes much larger than the standard composite kernel learning technique. And the thing is that with that technique, we can find even a better likelihood. But the problem is, even though it has a better likelihood, it overfits the function. As you can see there, that the approximation is worse and not slightly quite large, not quite large, but CKL is better than if you are using the composite kernel learning technique with full hyperparameters. Sure, it has more hyperparameters, but remember that it has more flexibility. So we need to be very careful. Remember the principle of Occam-Razor again. So that's why that based on our experiment, we avoided that overfitting by trying to keep the number of hyperparameters as low as possible. So in this case, we use the composite kernel learning technique because it only adds k hyperparameters. In that case, we avoid overfitting. And about more hyperparameters require more design of experiment. That might be true if you have a large of hyperparameters to tune, like in the composite kernel learning technique with full hyperparameters. But in that case, of course, we want to keep the number of DOE as low as possible. And for that case, we also need to keep the number of hyperparameters as low as possible. So we found that the composite kernel learning techniques with shared hyperparameter is the best option in this case. Or, oh, I'm sorry, if I want to add more, sorry if it's possible. Actually, we can also evaluate the AKIK information criterion or Bayesian information criterion to evaluate the resulting models. But I didn't do that in this research. But it's possible to use that information criterion.
Okay, thanks, Prem.
Yeah, thanks,
Any other questions from the audience? Okay, I had one of my own. You mentioned you have for the multi-objective Bayesian optimization, you had tried EHUI as well as the believer models.
Yeah.
And we have been doing some recent research trying to compare the two and finding that, and which is consistent with some other studies as well, where believer actually does quite well. I mean, even better than expected criteria often. So in your studies, did you find that kind of trend as well, or were there any other reasons to try both in your studies?
Okay, so in this study, we didn't try any other parallelization method. So Kriging believer came to our mind because it's simple. And I think based on some previous studies, actually Kriging believer performed quite well. So we didn't do that in our research, but because it's easy to implement in our Gaussian process regression surrogate model. So it's a nice heuristic and it worked, then we use that. So actually we also developed another parallelization technique with my colleague in Leiden University, with Thomas and Michael. So we tried that and it works better than Kriging believer. But I think at the time when this paper was written, so we have not yet developed that method. But again, I think one nice thing about Kriging believer is that it's simple. So it's easy to implement it with virtually any package of Gaussian process regression.
Last quick one maybe is, do you have, I mean, are some of these models available for like in public domain for research? If you want to try some algorithms on them?
Oh yeah, so this software, can you see my pointer?
Yeah,
It's available on GitHub.
Oh, okay.
Although I would not say that it's fully optimized, but some of our colleagues already using it, especially from Tohoku University. So they use this software to do many high-speed aerodynamic design case. So it has several capabilities. So it has capabilities for building a Kriging model with multiple kernels. It has capabilities for single and multi-objective Bayesian optimization by using expected hypervolume improvement and also Parigo. And it also has capabilities for uncertainty analysis, like for reliability analysis.
So that's on the algo side. I meant on the application side actually.
Oh,
for example, the Sonic application that you showed.
Oh, I'm sorry. You mean about
it's all right. Yeah.
The problem? Is it available?
Yeah, because often we do a lot of benchmarking on test problems, but it's then to sort of show the capability better, it's good to have some application or application inspired problems.
Yeah, that's nice. I mean, we discussed this a lot, right? I mean, like our community needs more real world test functions. Yeah, but unfortunately, for this case, we cannot share this to anyone. But we can share only the data of the experimental design, also the optimal solutions. And people can use that for benchmarking surrogate models, let's say. But for optimization, this case is not available, unfortunately, because like for the SBOOM software from NASA, they only shared that to a few people. We need to request their access for us to be able to access the SBOOM.
Okay, yeah, it's fair enough. There is one question in the chat. Maybe we can keep that as the last one. So basically, if hyperparameters need to be kept at low number, how to trade off the number of kernels combined? Is it a practical choice?
Okay, so thanks, Bang, for the question. The number of kernels combined. Okay, so the thing is that I think that you need also some kind of how do we call it? Some kind of knowledge here, because when I did this problem, so I know that there are some kernels that people use for engineering design. I mean, in engineering design, people use Gaussian, Matten kernels. Maybe some people use cubic, but people never use linear linear kernel functions in engineering design, or maybe other kernels such as, I don't know, such as the neural network, stuff like that. And we know that some kernels work better in our problems. So based on that knowledge, we only pick individual kernels that are frequently used in engineering design. So in that case, we don't need to use kernels that we know are not suitable for our applications. And I know that some people use even even use techniques such as genetic programming to evolve kernels. Because in that case, maybe they don't know like what kind of kernel that I should use, so they just use genetic programming to find better kernels for them. But I believe that if we already know that some kernels work in these particular applications, then we should pick those kernels in our composite kernel. So in that case, we can reduce the number of kernels that we use in our composite kernel. Then we also reduce the number of hyperparameters. So yes, it's practical, but we also have knowledge about which kernel to choose. So I hope that answered your question, Bing Wang.
Thanks, Prem. Yeah, we are over time now. Thanks for staying back for a few extra minutes. And thank you everyone for joining. And let me thank our speaker again on your behalf, on behalf of all the audience. So thanks, Prem, again.
Yeah, thanks to Heman and also the others for coming to this presentation.
Thank you.
So let me say something. Actually, I supposed to visit Canberra this year because I think I mentioned this to Heman last year, right? So if the COVID goes off, then I should go to Canberra because actually my wife received some scholarship to do a long-term visit in Canberra. So and I was planning to go to Canberra, but well, things didn't go well. But I'm glad that I can do this with, even though we are doing it online, but I'm very happy that I can share my research to Heman and also the students and also Professor Tapabra.
We look forward to having you in person very soon.
Yeah, so yeah, that will be my promise. I mean, after this thing goes off, then I'll visit Canberra for sure.
Okay, thanks, Prem, and thanks everyone. Keep a lookout for our future events as well. So they will be circulated through e-notice and newsletter, etc. So hope you all can join us also for the future series of the seminars that we organize. Thanks again. Bye, everyone.
Yeah, thanks, Heman, and thanks also, Ray. So bye-bye, everyone.
Bye-bye.
Hope to see you soon.
Sure.